Cool, let's do this. Yeah, welcome back to college algebra. This chapter 4 is going to go kind of quick, I think. And it starts with, let's get back to our library of functions. Let's see, maybe I'll write them all up here again quick. There was 6 of these. I'll make them kind of small. There was this guy. Do anybody know his name? And by the way, when I say his name, I guess I mean his equation. His equation is y equals x squared, right, you guys? Let's see, what else do I got? Oh, his cousin. His cousin is this one, which is y equals the square root of x. I'm going to go right here. I got this other one. I got this kind of snaky looking one here. That's good old y equals x cubed. So we discussed these back in chapter 3, actually. I asked you to memorize these shapes. Let's see, his cousin. His cousin is the sideways kind of version of him, which is the cube root of x. You know, that's the squaring, that's the square root. This is the cubing, and this is the cube root. Cube root of x. Cool. There's 2 more that are they're not related, they're not cousins. I'll put them here. One of them is this V-shaped graph, which is y equals the absolute value of x. And the other is this guy. This one that has, he's undefined here, he has an asymptote here, and he actually has an asymptote here. This is this one. And the graph approaches, oops, I'm in the wrong place. The graph approaches these asymptotes. It looks like this. And this is the only one that's got kind of a big undefined place. It's undefined when x is 0. That's why you have this asymptote. Oh, and his equation is y equals 1 over x. So now you can kind of see why he's undefined at 0. When x is 0, it's undefined. You can't divide by 0. So I'd like you to memorize those 6 basic shapes. But then what we start doing in 4.1 is we shift them or transform them. We can call these shifts or transformations. What does the book call them? Transformations of graphs. By the way, they bring up symmetry. I'm not sure. I'm not usually a big fan of symmetry. Symmetry is just something that's you can see or you don't see. I mean, look, like this graph. Do you see any symmetry? And we haven't talked about symmetry, so maybe you don't know what I'm talking about. So symmetry, like do you see some sort of mirror image? Or what would be the symmetric line? Or this graph is symmetric, and it's symmetric around the, I would say it's symmetric around the y-axis. Is that what it looks like to you? You see anybody else that's symmetric around the y-axis?
The absolute value.
There you go. He's symmetric around the y-axis. Right. This one's not, right? And he's not symmetric around the x-axis. He's not really symmetric to anything. Nope. Okay. This one's interesting. They call this, and this one too, symmetry. It's not symmetric around the y-axis, as you can tell. It's not symmetric around the x-axis, as you can tell. But it's symmetric around the origin, the point, the origin, which is a different kind of symmetry. This is symmetry around a line, and then this is symmetry around the point. Like, here's the deal. If you flipped it over and then flipped it upside down, would it land on itself? Flip it over and then upside down, and so it's symmetric around the origin. So this is some language in math that, you see it or you don't see it. You can test for it. I don't know. I don't see how useful it is. I'm not a big fan of symmetry. I mean, I see it, but I don't think I need to test you on symmetry. You kind of see it, I think. This might be symmetric to the origin too. If you flipped it over, yeah, these 3 are all kind of symmetric to the origin. That's interesting. Anyway, enough of that. That's symmetry. I want to shift these functions. Now here's the truth. If you take any function This is true about all functions, so it's true about all 6 of these plus any other damn function in the world. If you take any function and add some number to the to the end of it or in front of it, wherever you add a number, then then you have just shifted it up c units. You have shifted the graph, shifted up c units. If you take any function and subtract the c from it, can you guess what happens then? I'm talking about shifts. I use the word shift. We shift it. The book kind of uses the word transformations. Same thing, I think. We're shifting or transforming these things. So what happens when you subtract the c from it? Of course, it shifts down. Of course it does. It shifts down. And by the way, this is real obvious. I mean, it makes sense. It's not some mystery that I'm, believe me, have faith in this. It's very logical. Listen, what's the logic here? Oh, the function is like all the y values. And if you take all the y values and add some number to them, if you took all the y values and added some number to them, I think you move them up. The whole graph gets moved up. Or all the y values on the graph get moved up, which means the graph gets moved up. Or if you take all the y values and subtract some number from them, everything moves down. So this is real logical. Nothing too mysterious here. This one's a little different. The notation is a little different here. Now I'm going to take an x and I'm going to add a c, but it's within the function. So this c is not really added to the end of the function. The notation here is the c is kind of added to the x, which is the input of the function. So you're shifting the x, and you're shifting it left or right, and it's opposite of what you would think. So the plus c is actually a shift to the left. It shifts left c units. So now I guess I am asking you to have a little faith, because I didn't explain why. It's just the opposite of what you might think. So if it's an x minus c, again, added or subtracted to the x. This is different. You'll see the difference when I do an example, but maybe you sort of see the difference here. This is shifted to the right. Shifted to the right. One way to try to make sense out of that, maybe, is to try to say to yourself, I don't know, you just memorize it. You probably just want to memorize it. But if you wanted to try to make sense out of it, you could say to yourself, where's the new 0? If that makes any sense. The original function is some original function. And when x is 0, x is 0. But what's the new 0? I don't know if that's the right phrase. When x is 0, x is 0. What's the new 0? When x is what? When x is c, you get your new 0. So it's moved to the right, c. What's the new 0 on this one? When x is negative c, you get your new 0. It's been shifted. So your new 0 is when x is negative c. So that's shifted to the left, because negative c is over here on the left. Maybe you don't like that. Maybe you just better believe it. Couple more things. Stick a negative sign inside any function. Maybe we don't call this a shift. Maybe we call this a transformation. These are all shifting, up, down, left, and right. But stick a negative sign in front of any function. You probably know this one. Stick a negative sign in front of this. What happens?
Flips it.
It flips it upside down. Yeah, that's what it does. And that's true for all functions. We learned it kind of for parabolas, but it's true for all functions. Stick a negative sign in front of the function, and that flips it upside down. I'm going to say flips it upside down. That's what I like. Yeah. Flips it upside down. The book might say something a little more fancy than that. What will they say? They might say, oh, it's a reflection around the x-axis. That's what they might say. It's a reflection. It causes a reflection around the x-axis. But here in Ocala, we just say it flips it upside down. All right. What else? Oh, this is different. This is sticking a negative sign on the x that's the input to the function. So this is not a negative sign out in front of the function. This is different. This is negating the x, which, again, sort of takes the x and flips it. It flips the x. And so it flips it the other way. It sort of flips it sideways. Or, what's the fancy way to say that? It makes it a reflection around the y-axis. Or I like to just say flips it sideways. Yeah, that's pretty good. That might be about as much as I want to tell you there. It could get, ooh yeah, we could get a little worse here. Let me see. Yeah, all that stuff is good stuff here. All right, one more, I guess, one more. So this is one more. When you have a number a multiplied in front of the function, and we learned this with our parabolas, sort of. I mean, it was mentioned. Like if I put a 2 in front of this parabola, do you remember what happened if I multiply by 2? Like a 2x squared or a 4x squared? Oh, well, if it's positive, it opens up. But do you remember what the 2 or the 4 or the 8 would do?
Make it wider and narrow?
Yeah, which one? Do you remember which one it was? If it was a 4 or an 8? Or...
Narrow.
Yes, that makes it skinnier. It stretches it. It's kind of like it grabs those parabola ends and stretches it. So hang on. But that's only when it's a number bigger than 1. So what do I want to say here? I want to say if the absolute value of a, because I don't care about the sign, I just want the number. If the absolute value of a is greater than 1, that stretches the graph. And I called it making it skinnier. It stretches the graph or makes it narrower or skinnier. Stretches the graph. Let me just add that word, narrower. Okay, one more. If that absolute value of a is less than 1, which means like it's a 1/3 or a 1/5 or a 0.7 or, something less than 1. Then it makes it wider, but the word is compresses it. It's like it smushed it or compressed it and made the parabola wider, or any of these functions. Not just the parabola, but it makes it wider. It compresses the graph. So that gets a little tricky. Stretching and compressing gets a little tricky because your next question might be, well, how much does it, okay, it compresses it, but I don't know how much to compress it. Well, right, it's compressed more than the standard normal guy. This is the normal guy that kind of has a coefficient of 1. When that coefficient is more than 1, it's stretched and it's skinnier. When that coefficient is less than 1, it's compressed and wider. Do you know why I'm using absolute value? Because I don't care about the negative sign. Listen, because what does the negative sign do?
It just flips it.
That flips it upside down. If this is negative, that flips it upside down. So if it's a -3, don't call that less than 1. I mean, I know it's less than 1, but the absolute value of -3 is not less than 1. No, so if it's a -3, you know what the negative sign does. That flips it upside down. And then the 3, what does the 3 do? Stretches it, makes it skinnier. Right. If it's a negative 1/2, you know what the negative sign does. It flips it upside down, and the 1/2 makes it, compresses it, makes it wider. Right. That's pretty good, man. That's all kinds of shifting. And now, with those notes and these basic functions, good luck. I can ask you millions of cool questions, like sketch the graph of this. And when I say this, I mean without a graphing calculator. We can throw all those away nowadays. No, I'm kidding. You know what the funny thing is? I wish maybe, you know, the order, this book presented topics in a certain order. You know, we learned all about this in chapter 3, and it's a parabola, and his vertex is staring right at you. Remember I said his vertex is staring right at you, and I tried to make you memorize the HK format of the vertex. The vertex would be 7, 11, right, you guys? Mm-hmm. All right, well, the truth is, maybe all that would have sunk in a little better if I would have learned about shifts first. Because now, when I look at this, I want to write, can we describe what's going on here? I mean, first of all, it's an x squared function. So first of all, it's this guy, okay? And how has he been shifted? What's the plus 11 doing?
Shifting him up.
Thank you, up 11. What's the negative 7 doing?
Right.
To the right 7, that's right. According to my cool notes here, you're exactly right. To the right 7. Sorry about this faint blue. The 2 makes it a little skinnier, maybe a little bit stretched. But also, what about the negative sign? Upside down. It's a crappy looking blue. You guys with me? That's what, so when I give you a function, maybe you should make yourself little notes like that. That's what's going on. This is my basic function, and according to these rules, maybe I didn't give you too long to look at these rules. Maybe, do you understand? The plus 11 is out on the end of the function. That's this one. That's this plus c shifted up. That negative 7 is in there with the x. You can see that. It's in the function with the x, and it's shifting it to the right 7. That's this. The negative sign, of course, is out front, flipping it upside down, and the fact that there's a 2 there makes it sort of skinnier. That part gets a little vague. I just could try to graph it a little skinnier maybe. But here I go. With that cool knowledge, dude, I can graph this. And my main focus on the graph is sort of that vertex, but now I'm not even thinking about the word vertex. I'm just thinking about shifting. I'm shifting this graph to the right 7, up 11, and then I want to draw him. Wait a minute. He's a parabola, and he's been shifted over here, and he's upside down, and he's a little bit skinny. Dude, that's pretty darn good. I mean, that's pretty good, man. I mean, I like this section. You're when you master this, you're very powerful. You got a bunch of functions in your head, and you know how to shift them. I mean, you're powerful. You know a lot of stuff. I'm running out of board space. I hate to get rid of these great notes. Maybe I'll get rid of them though. Maybe I'll get rid of these. Can I get rid of these? I like them though. I like to refer to them, but you got them. Okay. Let's try another one here. What about this guy? I don't know. To me, there's a few things going on here. You should somehow, I mean, and maybe even on a test or a quiz, I'll ask you to describe the shifts or the transformations. So writing down these words, I think, is something I may even ask you to do. Not only might I ask you to do it, I think it's kind of a nice advice. Write down the shifts. What the hell is going on? The -4? Down 4 is a good phrase there. Down 4. The +3 there? That's the left 3. And that's really it. You know, the other thing to do is to identify, you know, which one is he? He's the cubic function, of course. He's the cubic function. You know, maybe that's my name for him. He's the cubic function. I've got his shape memorized. He is this one. But I'm shifting him. Now, listen, I'm shifting the whole function. I'm shifting the whole function, but the way to do it is kind of maybe focus on this point and shift this point and then draw the function. That's kind of what I did with my parabola. I shifted, you kind of focus on that center point or that 0 point. Okay, so what did we say? I'm going to draw a quick graph. This guy gets moved down 4, but over to the left 3, to the left 3. All right, hang on. To the left 3, down 4. So here's the kind of the center of him, and now I should sort of draw my cubic shape. He's not upside down, is he? No. No, this is it. He's just this cubic shape. Yeah, I'm not sure how accurate I did. You know, it's kind of rough. If I really wanted some more accuracy, I could plot more points. I'm trying to teach you how to do this without plotting a lot of points. Just want to try to learn about basic shifting. So, you know, I don't think it's difficult. And I got a lot of ways I can ask these questions. I don't think it's difficult, but it is kind of a bit to memorize. First of all, 6 functions to please memorize, and then that, you know, that list of transformations, memorize how that works. I mean, you memorize it, but it's also very logical once you practice it a little bit. So, I don't know. I can ask these kind of backwards too. I mean, sometimes, watch this. Here's a picture. So here's a picture of a function. So now, this is backwards. Now, instead of giving you the equation, I'm giving you the picture, and I want you to come up with the equation. Can you come up with the equation for this? Well, which one is he?
Oh, he's the absolute value.
He's the absolute value. That's who he is. Let's see. So I should put some absolute value bars. Look, that's partial credit. Let's see. Anything else going on? Let's see. How's he been shifted? He's been shifted up 47. Do you agree with that? Mm-hmm. He's been shifted up 47. So I should just put a big old plus 47 out on the end. And what else?
He's been shifted to the right 85. So you want negative 80.
To the right 85. So you know, this is an absolute value of x, but what should go in here with the x? A minus 85, like you just said. Some students, there has to be a variable x, and then it's shifted to the right 85. That does it. That pushes it up 47. This is beautiful, except for one more thing.
It's inverted.
It is flipped upside down. It is flipped upside down, so stick a negative sign in front of it. Right. There's no way to really gauge how narrow or wide he is, so I can't really put well, don't forget to put a 2 or a 3 out front. I mean, we can't do that. We're not. So this is, I'm ignoring the narrowness or the wideness here. I'm just working on the shifts because I can't really do that. Yeah, that's awesome. Give you a picture, make you come up with the equation, or give you the equation, make you come up with the picture. Yeah, those are good questions. You know, the other thing that could come up here, then I could ask about x or y intercepts, I suppose. I might lay off that for a little while. But I might ask for domain and range. That's kind of interesting sometimes. Well, let's look at this guy. Can you tell me his domain? What are you allowed to plug in for x?
Everything.
And maybe you're looking up here, or maybe you're looking here at the picture after, you know, I don't know. You can stare at the equation, or you can stare at the picture after you've drawn it. I always said that domain and range is easier after you draw the picture, because then you can see. But he's right. This thing, you know, it's a skinny snake-shaped cubic function, but it does spread out over all x's. So the domain is all real numbers. The range might even look a little easier to you. What do you think the range is? I mean, those arrows tell me that this thing's going up forever and down forever. I think it hits all y values. I think the range is negative infinity to infinity. I mean, it's clearly going up and down. It is also spreading out, of course. So that domain and range was obvious, maybe an easy. This one's a little different. What's his domain?
All real numbers.
It is. It spreads out over all x's. You're allowed to plug anything in for x. Negative infinity to infinity is your domain, but the range is a little restricted. You know, similar to our parabolas we just got done studying. This guy has a maximum point, doesn't he? He has a maximum point, and the range would be
47 to negative infinity.
47 to negative infinity. I write that backwards, though. I don't say it. I mean, that's cool. It's negative infinity to 47.
Right.
Right? It won't go higher than 47. Right. And the picture sure helps. Right. I'm not looking at this equation. I'm looking at these. Domain and range are easy when you look at these pictures. Here, let's do another one. This one, I mean, this is just another one, but somehow I think sometimes this bothers students a little more. Let's watch this. Let's see here. Well, let me think here. Okay, again, I want to write down some notes. I mean, I want to sketch the graph. I mean, what's my directions? I think my directions are sketch the graph, maybe tell me the domain and the range, and maybe my other directions are describe what's happening to this function. So use some words, write down some words describing these shifts. So what would you say? Like I've kind of been doing that. What would you say?
It's shifted up 32.
It is shifted up 32. Now maybe I threw you off a little bit. Listen, you know, the way these, oh, I lost my directions. When I had my directions, my notes, you know, I wrote it like this. You take any function and you add a number out on the end, and that shifts it up. Well, instead of adding it on the end, this time I added the number in front. I mean, you can add a number to the front or to the back of a function. That's how addition works. You can add in any order you want. So that positive 32 is added to the function. That positive 32 is added to the function, and so it is a shift up. Are you guys okay? Up 32, that's what he is. The 13 is clearly in there with the x, don't you think? It's clearly in there with the x. I know there's no parentheses, but it's inside the square root. There could be parentheses. It's in there with the x. So the 13 is left, huh? 13 left 13, okay. All right, so that's cool. Anything else? That negative sign makes it upside down. That negative sign makes it upside down, okay. All right, dude, so can I draw this? Oh, by the way, which one is he? He's this square root function. Where is he? Yeah, he's this one. All right, so the square root function shifted to the left 13, up 32. Yeah, I got this. To the left 13, up 32. And it's cool to label it like that because then, you know, that helps me know you know what you're doing. And then I'm ready to draw it, except it is upside down. So I'm going to try to draw this upside down shape here. See it? Be careful with this shape. Listen, what this shape doesn't do is it doesn't do this. It doesn't come back up. So don't draw it too loosely and crazily. Try to be a little accurate here. It does actually continue to decrease, actually. Right, that's what this does. It continues to slowly increase. It doesn't come back down. You guys okay? Shifting the square root function. We did a good job. Now, after he's done, can I answer these questions? The domain. The domain is the x values. And this is, you know, a lot of these domains are all real numbers, not him. But not him either. His domain, he stops and sort of starts right there at that end point, which has now been shifted. So I think his domain is all x's greater than or equal to negative 13. Or I could say that a different way, but that works. Yeah, right. Greater than or equal to negative 13. And the y values are the range. And I think the y values are less than or equal to 32. Do you agree with that? That's my domain and range, especially after you see the picture. It's easy. Okay, cool. All right, so I'm going to move on. I'm going to kind of go into 4.2. So it's kind of a different topic. So let's go to a different topic here. In 4.2, I'm doing this funny thing. I'm combining functions. So check this out. This is a little funny here at first. I'm going to here's a function. That's a function. Here's another function called g. 2x squared minus 3x plus 1. So I got these two functions. So what they teach me in 4.2 is that I can combine functions. I can combine them in a lot of different ways. Now, all right, so I can add the two functions together. Now, that's so darn easy, I don't even want to do it. I can add these two functions together, which if somebody told you to add these functions together, what would you do? Can I say that you would start combining like terms? Is that what you would do? You would add these functions by combining like terms. Okay, thank you. It's easy. All right, what about subtracting them? Kind of the same thing, although students always bother me when I do subtraction. Let me show you. So let's skip the addition. We'll do the subtraction. So I'm creating a new function by subtracting the two functions. And what this means is it's f of x minus g of x. And then, you know, people can subtract, but people make mistakes when they subtract. Do you know why they make mistakes when they subtract?
They don't subtract the whole function?
Yeah, I think when you subtract a function like that, you better put it in parentheses because you better distribute the negative sign. And when you don't do that, that's when you make a mistake. So I'm taking one function, f, and I'm subtracting g. That's what they told me to do here. And now I'm writing it out a different way here. I'm taking f and I'm subtracting g. I wrote it out here. Let's do it. When I do it, I get a negative 2x squared. When this negative sign distributes, it will be a plus 3x. Plus 3x plus this 3x will be plus 6x. When the negative sign distributes, that's a negative 1. A 7 minus 1 will be a 6. And you're done. Well, he's not doing it. But the point is, when you have two functions, you can combine them, and when you combine them, you get a new function. So we created a new function. Look at it. This thing is not f. He's not g. He's not f. He's not g. He's this new thing. You know what he's called? F minus g. Or if you wanted to give him a new name, call him h or l, or, you know, he's a new function. Give him a different name. But you could call him this. He's called f minus g. All right, anyway, adding and subtracting. I mean, we've done some adding and subtracting because we have to do the profit function is the revenue minus the cost. We've done some subtracting before. Let's see, what else can you do? Add, subtract, you could multiply. And the notation for that is, watch this, f times g of x. But what that means is, and I put a dot there, this is, I emphasize the dot, because it's multiplication. I mean, I guess the truth is I could just have them kind of next to each other there. But anyway, f times g of x, which means f of x times g of x, which is a bit of a pain in the ass. I mean, this is 3x plus 7 times 2x squared minus 3x plus 1. I mean, this takes a little work. Not only do you have to FOIL, in fact, FOIL might not even be a good word here. It's a binomial multiplied by a trinomial. It's a little more than FOIL. It's everybody times everybody. You know what I mean? I mean, I got to take the 3x times everybody. I got to take the 7 times everybody and collect like terms. I mean, it's just multiplying. It's not hard, but it's lengthy. But when you do that, you create a new function. Here, let's do it. 3x times 2x squared is 6x cubed. Do you agree with that? 3x times that negative 3x is negative 9x squared. Gotta be careful. 3x times a 1 is just a 3x. So I'm done with the 3x. I multiplied them by everybody. Now here comes the 7. 7 times 2, that's 14x squared. 7, negative 21x, and then a positive 7. See, it's lengthy, and then you can combine like terms, and you'll be done. This is, 6x cubed. Those x squareds can add together. That's a 5x squared. Those x's can add together. That's negative 18x plus 7, I think. Yeah. And you created a new function. You created a hell of a new function. When you multiplied those two original functions, we got this new function. Guess what? You can divide functions. I'm not a big fan of that one. There's kind of not much to do. Like if I was dividing these functions, you create a very, well, you get f divided by g. And there ain't much to do there, okay? That's kind of it. So, I mean, you can't actually divide, really. So we're done. We created a new function called f divided by g. I tell you what, though, here's one place where the division is helpful. You know, when you have a cost function, like maybe 4x minus 7x squared, maybe that's the cost of building x units, right? Remember, x is the number of units. And this would be the total cost. Like if I let me just change it to plus. Like if x was a 10, you know, if I had to build 10 of these things, I could plug a 10 in and I could tell you how much it cost. Total cost, do you hear me? The total cost to build 10 things. Or build 20 things, plug in, it's the total cost to build 20 things. Okay, what if you wanted, they do this to you in this section. They do this thing called average cost. This is total cost, let me say this. This is total cost. But average cost would be per unit. So it'd be, I think you should take, let's see. If it costs $700 to build 10 things, the average cost would be the $700 divided by the 10. You following me? If it costs $700 to build 10 things, then the average cost would be the 700 divided by the 10. I think it would be $70 per unit. Does that make any sense? Except I've got per. But, so, average cost. They use this symbol. They put a bar over it to call it average cost. And here's what it is. It's the good old cost function divided by x, which is sort of what I just said. The total cost, well, I use numbers. This is it in general, with variables. You get the total cost function and divide by the number of things you built. And that would be the cost per unit, or the average cost. I'm trying to say it makes sense. Do you agree it makes sense? Total cost divided by each unit would be an average cost. So watch how you do that. So if this is my cost function, what do? You take your total cost and divide by x. So just in general, I did it over here with numbers, but in general, you take your total cost function and you divide by x, and you know how to it's easy to divide by just an x because you can actually divide the x into both these terms. I'll tell you what, it'd be bad if you only did one of these though. I mean, the whole thing is divided by x. So anyway, what's the 4x divided by x? 4. What's the 7x squared divided by x? You cancel one of the x's. You cancel one of those x's, leaves you with a 4. You also cancel one of those x's and leaves you with 7x. This is your average cost function. Not a big deal. Shouldn't be a big deal. Okay, listen. So what was I doing? Combining functions. Okay? So what did I do? Add them, except I didn't add them. Adding, I can add them, I can subtract them, I can multiply them, I can divide them. That's what you can do with functions. Just what you do with numbers, that's what you can do with functions. You can add, subtract, multiply, and divide. Except with functions, there's one more thing you can do. You ready? One more thing you can do. The add, subtract, multiply, and divide was just sort of a build-up. I don't know how useful it is. It's useful at times. That's kind of useful. But the other thing we can do, add, subtract, multiply, and divide, the other thing we can do is this thing, compose. It's called compose the two functions. Or it's called doing the composition of the two functions. And here's what it is. The notation for composition is a little circle. So I'm doing f circle g of x. And that little circle does not mean add or subtract or multiply or divide. It doesn't mean any of those things. It means compose. And what the hell does compose mean? I'll show you. It means this. It means f of g of x. And when I write it like that, some students think, oh, they're next to each other. That is multiplication. No, 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 no. This is function notation. And what this says is that g of x is the input for the f function. What composition is it's taking one function and plugging it into another function. That's not multiplying, adding, subtracting, or dividing. That's composing. Plugging one function into the other function. Here, let's try it. How the hell do I compose f of g of x? According to this, I'm supposed to take g and stick it into f. All right, hang on. That means take g, the entire g function, and stick it into f. Where do you stick it? Thank you. That's where you always stick stuff. Right, you stick it there, and then you get 3 times that entire damn plus 7. You see what I did? I took the entire g function and stuck it into f. It's called composition. It's kind of a new idea, maybe. I mean, I don't know. You guys have done a lot of algebra, but this might be a new idea. I'm going to clean it up. When you clean it up, it just becomes whatever it becomes. 9x plus 3 plus 7. Right, it becomes some new function. When you compose it the other way, let's try it the other way. G circle f of x. And here's what that means. It means g of f of x. And when I read that, I'm good at this. Listen, I read that and I say, okay, I got a g function and it's got something is the input to the g function. What's the input to the g function? The whole entire f function. They're asking me to take the f function and stick it in the g function. That's what that says. I can read that. I know how to read that. Take the f function and stick it into the g function. Okay, let me try this. Hold on. That's backwards. Now what am I doing? I'm taking the f function and sticking it into g. Hey, where do I stick it?
X.
Into x, which is there and there. Right, you guys? So here I go. I'm going to have 2 times something squared minus 3 times something plus 1. And what am I sticking in for that something? The f function, 3x plus 7. You guys with me? That's composition. And you can clean that up. That's algebra. I should do it though. You know, to clean that up, I have to FOIL this. I'm so good at foiling. I was foiling champion in kindergarten. You ready? That's a 9x squared plus a 42x plus a 49. That's what happens when you FOIL that. When you distribute this, it's a negative 9x, negative 21 plus 1. When you distribute this to, it's 18x squared plus 84x plus 98 minus this 9x minus 20. Okay, so that's 18x squared plus 75x plus 78. I combined all my like terms. I'm finally cleaned up. I'm in a hurry in case you can't tell. People FOIL things wrong. I FOILed this. I FOILed it real quickly. It's 3x plus 7 times 3x plus 7. I FOILed it all out in my head, and that's what I get. Some people FOIL things wrong if they do it too quick, so I don't want to. You got to do it right. But anyway, we created this new function. Hey, we're combining functions, but now we're focused on kind of the new idea of composing or composition of two functions. One more thing. So it's kind of, what I'm doing here is I'm composing these functions in general for any x. It's kind of fun when you have this problem. Watch this problem. F of g of 0. See, when you have a specific number to plug in, it's a little more interesting, maybe a little more fun, but it's a little two-step problem. See, what does this say? It says, take 0 and plug it into g. If I read my way inside out, which I think I should do, it says take 0 and plug it into g. Well, you can do that. When you do, you'll get an output, you'll get an answer. And guess what, though? What will you do with that answer?
Plug it into F.
Plug it into F. That's what this says. So it's a little two-step problem. Let's try it. If you plug a 0 into g, it's easy. You plug a 0 into g and you get 1. So the output here is a 1. And now what do I do with that 1? I plug it into F. And this turned into a 1. And now I plug it into F. 1 times 3 plus 7, the answer is 10. It's a little two-step problem. It's composition. I did it in 2 steps. You know, I could have done it in 1 step. Did I already compose F with G? Did I already compose F with G someplace? Yes, I did. Right here. See it? So you know what I could have done? I could have plugged in 0 into my F composed with G thing. My F composed with G function is right there. If you plug a 0 in there, what do you get? 10. I like the two-step process though. Plug 0 into G, get your answer. Plug that answer into F, get your final answer. Okay. I think I'm finished. But who knows where